Hi guys, this is 706 where we're going to start talking about conservation of energy, and conservation of energy is going to be a multiple part video series just because it is such a big concept in not only physics but especially in the AP physics. So we know that what's going to happen is, so let me go back. We did our energy bubbles, if you remember way back at the beginnings. We had mechanical energy, and then we had thermal energy. We had, I'm just going to do three of them. So over here we have thermal. And over here we had sound. And we said if we had friction, that the energy tends to bleed from this bubble to those bubbles. So when we talk about conservation of energy, we can't just include the mechanical energy that is going to stay in the bubble. We also have to consider what's going to leave the bubble. I'm going to start writing some equations. We could say that our energy initial has got to equal our energy final. And in this equation, we have to add in plus the work, and we're going to put in NC. So WNC stands for work not conserved. And I'm going to do a little red box around this. And that means that we're talking about any of the energy that flows out into the other bubbles. So we have to take this into account. We're going to write this out long ways. We would say the initial energy. And whoops, spelled that wrong, and I'm not going to start a re-record. Initial energy, remember energy is a capital E, equals the final energy plus the work not conserved. So long form, that's what we're looking at. And we can use this to our advantage in a lot of different ways. And today what we're going to do in this video is we're just going to look at some scenarios. You have to put in, though, you have some ground rules. So we're going to look at three different scenarios. The first thing you have to do, number one, is define your system. The second thing that you have to do, number two, is you have to define your 0 point. Define your 0 point. And then the third thing you're going to do is an energy analysis. An energy analysis. What do I mean by energy analysis? I want you to imagine you're at the supermarket and you're looking at the shelf in the supermarket. And you're going to buy a box of energy. And there's choices. So we've got gravitational potential. We've got elastic potential. We've got kinetic energy. It's an E. Sometimes we're going to have energy that doesn't want to stay in place, so we're going to have work not conserved. Later on, we're going to have, so I'm going to do this in a different color because this is going to be later when we get into rotational motion. We're going to have kinetic energy rotational, and that's going to be translational. So what you have to do when you're looking at these problems is you have to look at what you're starting with. Maybe you have this and this to start with. Maybe you only have this. Maybe you're moving and you're going to go up a hill, and so you start with this. So when we go to write the equation for conservation of energy, this is about as good as we can get in terms of an equation that we can use over and over. What you have to do is you have to go to the grocery store. You have to pick off the shelf what you're starting with. You have to pick off the shelf what you're ending with. And I call that energy analysis. So let's take our first example. Let's say we want to analyze the energy. So let's do sample A. Let's do a spring launching a ball into the air. Spring launching a ball into the air. All right, so I'm going to do a spring. It's going to be compressed. Here's my ground. And then on the second scenario, the spring's been released and the ball is in the air. And we want to analyze the energy. We want to use conservation of energy to analyze from here to here. So I suppose one of the sub things we could put in defining your system is this, what will be included here is your start and end point. Start and end point. And remember, energy is scalar, so we don't care what happens in between. And what I want to do here is I want to create a conservation of energy equation for each of these scenarios. So we've got initially, so let's define our system, and I'm going to use red. So if I looked at a free body diagram of this, I would have, at this point in time, I have a spring force and a potential spring force because I have a compressed spring. So this represents US, so spring, or I'm sorry, UE, elastic. Now, do I have gravitational potential energy? It depends on where I set my 0 point. If I said this is 0 point, yeah, I've got a little bit of gravitational potential. So what would make sense would be to set 0 here. Let's set the ball's initial height here. So we're going to set that as 0. So now I don't have any initial gravitational potential energy. Again, if I had set it down here, I would have, and I would have had to have taken that into account. So my initial energy is a spring force. So let's assume that this ball is at the top of the flight path. We're going completely vertical. And remember, at that top of the flight path, for that split second, we don't have a velocity. Our velocity is 0. So that means I do not have any kinetic energy here, because 1/2 mv squared v is 0. But what I will have is gravitational. I will have UG. So I can say that for this system and in this scenario, I can say 1/2 kx squared is going to equal to mgh. So now I have a conservation of energy equation for this system. Let's go on. Let's look at scenario 2. Let's do a letter B. And let's do a cliff. And let's do a ball on the cliff. And we're going to ignore air resistance. And the ball is going to fall to the ground below. So let's define my system. And we're talking about, so our scenario is what is going to be, let's go, let me write it out. Ball in free fall. So we've got a ball in free fall. I'm ignoring air resistance. So once I go into free fall, the only vector I'm going to have, force vector, is going to be the weight of gravity, and that's included in the system. So I don't have to worry about any non-conservative work. And I forgot to mention that in the last example. The reason we're defining that system is we're trying to figure out if we've got any work not conserved. So for the first scenario, no. And for the second scenario, no. Well, so starting off, do I have any spring potential energy? Nope. Do I have any kinetic energy? Nope. Do I have any work not conserved? Nope. But I do have gravitational potential energy. So starting off, I'm going to have UG, and we're going to analyze it right before it hits the ground. So we're talking about my start point is when it launches from the cliff. My end point is just before it hits the ground. So I'm going to have kinetic energy when it hits the ground. So my equation, my conservation of energy equation here is going to be mgh equals 1/2 mv squared. All right, let's do one more. Let's take a spring that is against a wall, and we've compressed it. So I'm going to show a compressed spring. So this is before. And we're going to put a ball next to that. And then after, the spring is going to be uncompressed. And we're going to look at the ball is traveling along the surface at point X. So we started off, we had a ball next to a compressed spring, and then we're going to look at this when we are here. And we are not assuming that friction is ignored. So this is on a surface with friction. So the ball is on a surface with friction. Okay, so if we look at my starting scenario now, so this is going to be my system. And it's worth noting, it's kind of good sometimes to draw out the system when you are in both scenarios, because we have a little bit of a different happening here. So my normal force, my weight vector are within the system, because I'm going to do the ball, spring, ground. So those are all internal. So everything, all my forces here are going to be internal. Over here, if I'm doing ball, spring, ground, look what happens. I now have friction. So if my ball is moving this way, if I'm moving that way, and friction is going to go this way. And so look, now I have a force that is external to the system. So when I write my equation, I have to consider work that's not conserved. So starting off with, I've got elastic potential energy. And at the end, I'm going to have to do work not conserved. And what else do I have? I'm moving. So I'm going to have kinetic energy, and I'm going to have work not conserved. So when I expand this formula, that's going to give me 1/2 kx squared equals 1/2 mv squared plus work not conserved. And the work not conserved is coming from friction. So I could even expand this further to say 1/2 kx squared equals 1/2 mv squared plus coefficient of friction times the normal force times distance. Because remember, work is force times distance. So force of friction is always equal to the normal force times mu. Okay, so that just kind of shows you really the highlight here was how do we do energy analysis? That's what we were doing in these three problems. And anytime you come to a conservation of energy situation, you have to do an energy analysis, and you have to get pretty good at doing this. I just realized that I was a little off screen here. So, all right, you have to get a little speedy at doing these as well. All right, so let's do sample problems in parts 2 and 3.